sigma xy, the whole conductance is NE squared over H. Okay. Now remember that compared to the one-dimensional case, we do not have factor of 2. The reason is that the factor of 2 arises from spin up and spin down the Grove freedom. But here we have strong external magnetic field. So the spin of the electrons are fixed. Okay, so we don't have this factor of 2, but still it is E squared over H times integer. Okay, why? Now, why? Now we thought that we understand what happened in one-dimensional conductor, but now here we have a whole device. We have external magnetic field. Especially the system is not one-dimensional, it becomes two-dimensional. But still, we have similar formula. Why? And if you could explain this, it may not give you Nobel Prize, but it will get you professorship in Harvard University, I guess. Okay, to explain why this is so. Now, the best explanation was given by general agreement given by Laughlin. So again, I take this diagram from Laughlin's Nobel lecture. The title is Fractional Condensation. And Laughlin said the following. He said that let's consider the Gedanken experiment. Because, okay, before we had two-dimensional electron system. Now I make the two-dimensional electron system into a cylinder. Okay, so the flow of the electron is around the ribbon. Okay, can you see? Okay, right? Okay, so it just make the system periodic. Okay, so we would like to understand why I over V is a constant. Okay, it's N times E squared over H. And Laughlin said, if we adiabatically put a flux through the center, as you can see clearly in this diagram, through the center, the effect of that adiabatic process is to move one electron from the left edge to the right edge. How did he argue that? But suppose that we first accept this. Okay. You put a magnetic flux through the center by adiabatically turn on and turn off the magnetic field. You can calculate the current in this way. The current will be the C is the speed of light. Up to now, we haven't seen any speed of light C anywhere because I set it equal to 1. Okay, but never mind, because the C will be absorbed into the so-called flux quantum. Okay, the flux quantum usually will be H over E or E over H, and with C you just H over C E or anyway. So this formula is from E and N, or it is from E and N or thermodynamics. Okay. You just calculate the change of the energy in the system and divided by the change in flux. And because the change of the energy is just the energy difference between if you move an electron from the left-hand side to the right-hand side, and since the potential difference is V, so the change in energy will be EV. If you transfer n electron, there is an extra factor of n. And then you just calculate this, then the answer just comes out right. Okay, okay, let me come back to why Laughlin said that in this adiabatic process, an electron moved from left edge to the right edge. That is, okay, the way he got this is he examined the wave function. Because of the wave function, you can obtain the wave function explicitly. If the system is clean, you don't worry about any impurities, things like that. Okay, interactions. You just have free electron and external magnetic field, and so this you can solve the equation exactly. Okay, and you can see that if you just change phi, then the center of the wave function, you have to have some knowledge of, for example, Landau solution to understand what I'm saying, but for the moment, you just have to trust me. Okay. The wave function, the center of the wave function in the Landau gauge will shift by certain unit. So Laughlin used this diagram to say that, okay, the electron left this edge and moved to the state next to it. And the state, the electron in this state moved to the state next to it, so on and so forth, till the electron here moved to the right edge. And this argument is, some would say, brilliant, but it's also, I would say, not completely transparent, at least to me. Okay, I mean, okay, this is great. Laughlin argued that, okay, he showed you that, yes, the experimental result could be understood through this Gedanken experiment. But still, somehow, I feel that I do not understand it completely until I can use chiral analogy to reinterpret his argument. Okay. So let me again quote an also very influential article by Harpring. And the title, this is in Physical Review B. Physical Review, at that time we have, okay, yeah, this is B. Quantized Hall conductors, current carrying edge state, and the existence of extended state in a two-dimensional disordered potential. Okay. Lastly, Harpring expounded further the significance of Laughlin's argument in this way. Harpring said, suppose that this is the band, the strip, okay? And we know that at the edge, we must have some sort of confining potential, or otherwise the electron will escape, right? And since the electron is confined within the strip or the ribbon, there must exist confining potential. And so that changed the Landau solution a bit, because the ideal Landau solution is for infinite space, right? Two-dimensional space. But Harpring said that if you look at the energy level in this system, it will be like this. Without the edge, it will be just the usual Landau level. Okay. So inside the bulk, you have gap. So gap flow in the bulk. And that is why it's an important feature in the discussion of topological insulator. Gap flow in the bulk. Now at the edge, because of the confining potential, it is gapless. So if I use the Harpring's picture, or Harpring further even discuss, if you have disorder, impurities in the system, then it will localize the bulk state, okay? But still could not change the gapless edge mode. We will see in some cartoon now. Okay, next. Now. So what Laughlin said is that if you put a magnetic flux through the center, what you have is to move one electron from the left edge to the right edge, right? From the left edge to the right edge. You could also move two. Okay, it depends on how many branches. Okay, for each branch you can move one, and that is precisely the picture I just tell you about in the one-dimensional conductor, right? Except that in one dimension, the left moving or right moving particles are on the same line, okay? But in quantum Hall effect, the left moving or up moving, right moving or down moving channels are spatially separated. They are not together, they are separate spatially. So we can see that why the formula is the same, E squared over H times some integer. Okay, because the physics is the same. The physics I explained, which is good for one-dimensional chain, that is one-dimensional conductor, is also good for quantum Hall system. So you have the same result, okay? And why the Plato is so exact, so precise in the quantum Hall case? First of all, if you have impurity along the edge, then it will just skip around it. Okay, there is no way to have backscattering. To have backscattering, the right moving particle must jump to the left moving branch, and because they are spatially separate in space, so there is extremely small probability allowing to do that. So that's why that this is very robust, much better than one-dimensional case. Because one-dimensional case they are together, so you can imagine that it is easier to have backscattering. Okay. So again, you can. I suppose that you have seen this picture many times. Okay. You have skipping motion along the edge, but cyclotron motion in the book. Okay. So what Laughlin proposed, of Laughlin's brilliant argument, now I interpret it as just saying that we have chiral anomaly in the system. Okay. So the most important message: the left or up moving, right or down moving electrons are spatially separated. So no backscattering. So quantum Hall effect is robust. So I guess that I have tell you what I want to say. That is, I promise you that I will explain the left diagram. Okay, what this means. And I leave the more difficult task for explaining the right hand side to other lecturers. Okay. Now, before I finish, oh, this is not important. This is important, but this is my task. Okay. So this is the quantum Hall system. You have a magnetic field, and you also have skipping motion. Okay. And so this is with magnetic field, and the time reversal symmetry is broken. Now, the interesting thing about topological insulators is that you can achieve that even with no magnetic field. Okay. And you need spin orbit interaction, so on and so forth, to achieve that. Okay. Now, I will just spend 3 minutes on Chern-Simons, okay? Because some of you may already heard about such thing in the literature. Saw such terms in the literature and wonder what that is. And I think I should spend just a couple of minutes on this. Let's begin with the ABG anomaly. Remember that the ABG anomaly said that D mu J mu A is equal to that. Remember this? Okay, this is E dot B. Do I need to go back to the original transparency? Okay, so you know this. This is in 2+1 dimension. Yes. Now, this subject. So this is, as I said, E dot B, electric field dot magnetic field. Turned out to be a total divergence. It is a total divergence of this subject. So this is D mu epsilon mu nu alpha beta A alpha D beta A gamma. If you suppress one index, then originally mu alpha beta gamma refers to 0, 1, 2, 3. If you suppress one, it becomes a three-dimensional animal. Then you define the so-called Chern-Simons term in 3 dimensions. So that is epsilon ijk ai dj ak. Now this is the abelian case. So again, this is formal stuff. Okay, just in case you didn't know before, I define the Chern-Simons term in this way. Okay, it arises in mathematics from this. Okay, more or less. Okay, it really arises from this. That is, this is the derivative of something. This is d of something. This is the exterior derivative of something. If I write this formula in differential form, okay, so this is Chern-Simons term. Okay. The important thing to notice is that the Chern-Simons term just contains one derivative. Okay. In comparison with Maxwell's term has 2 derivatives, partial A, partial A. So this has only one derivative. That was the non-abelian case. If we look at the non-abelian case, because this formula can also be extended to non-abelian case. In the non-abelian case, the F mu nu will carry an extra index, the group index, okay, or D group index or D alpha index, whatever, okay. And the anomalous piece is turned out to be also a total divergence, okay, also D of something, and that something also define the so-called non-abelian Chern-Simons term, okay, and it is something like this. And I show this because you can sometimes, or rather often, read such terms in literatures on topological insulators. Now, if I define the so-called Chern-Simons Lagrangian by this, so I'm just looking at the Chern-Simons, the non-abelian Chern-Simons term, and using it as a Lagrangian. This is very peculiar because ordinarily, a Lagrangian, the kinetic part to this should contain 2 derivatives in field, in your field. But here, the Chern-Simons term just contains 1 derivative. So it has a very special property, but I do not have time today to tell you about the properties of Chern-Simons term. Okay. But anyway, so it is a peculiar theory. Okay. But anyway, topological insulator is a peculiar thing, so need a peculiar theory to describe it. Anyway, okay. So under non-abelian gauge transformation, A mu goes to this. Okay. So this is standard Yang-Mills gauge transformation. Then this Lagrangian will not be invariant. It is strange. It's interesting. It will not be invariant. Unlike the usual Yang-Mills type gauge theory, which are invariant under gauge transformation. The Chern-Simons theory is not invariant. But the second part is okay. Okay, so the Lagrangian change, okay, had extra 2 terms. This part is a total derivative. So that's okay. If you impose appropriate boundary condition, the second part can be got rid of. Okay, but this part, if you integrate over a 3-dimensional space, it will becomes an integer. So this part, remember that. Okay, so everything times k is a parameter, the coefficient of the Chern-Simons term. So if you integrate this over d cube x, because this is Lagrangian and we are interested in action, so you need to integrate over d cube x. As I said, that because this is total derivative, so we don't worry about this after integration over 3 space. And if you integrate over d cube x, this will not vanish. It will give you integer, okay? And proportional to k, it will give you a pi squared times some integer n. N refers to the so-called winding number of the G. G is the an element in group. So the Chern-Simons action will change by a factor to a pi squared times k times n. Now we know that in quantum physics, what is important is not s, but e to the is. Of course, if I put in h bar, it will be I over h bar s. So even though s is not invariant, as long as e to the is invariant, it's okay. So this extra part, if it is 2 pi n, so e to the I 2 pi n is equal to 1. That's okay. So that means that k must be some integer over 2 pi, right? If this is put into this, it will be certainly of the form 2 pi n. So the interesting thing about the so-called Chern-Simons theory is that the integer, the coefficient must be quantized. Okay. And I think that I should point out this to you. Okay. It may or may not help you in reading papers, but I'm way over time. Okay, I should finish in 3:30, but I'm already 20 minutes over. Okay, I will stop here. Thank you.
Okay, since we are late for the break, so we will postpone. If you have any question after the break, Professor Kao will still be here. So in that discussion section, we can ask him. And now we will have 15 minutes break, and the coffees and the cookies are ready.